Now that we've talked about collision theory and ionic bonding, I want to talk to you about covalent bonding. Now, covalent bonds form between two non-metal atoms. Compare that to what you know about ionic bonds, which form between a metal and a non-metal. Now, it's the attractive force between a pair of valence electrons and the atom's nuclei that leads to this bond formation. It leads to this formation because it's more stable. I want you to think about the example of diatomic hydrogen. If you consider each hydrogen individually, they have one valence electron. And you know from our studies of electron configurations that the more stable configuration would be with two electrons in the s subshell. That would give it a full stable structure. So if each one of these atoms come together and each shares one electron with each other, then they form a more stable molecule, and that is exactly what is happening with covalent bonding. If you take a look now at this animation, you can see that when they are apart, and each one of these is showing one electron moving around. When they come together, they form almost one entire electron cloud where those outer electrons are being shared. And again, it's their attraction to the nucleus that ultimately leads to the formation of these clouds. Now, if you look at the difference in electronegativities for covalent bonding, you're going to find values that are less than 0.5 on average, and that is for a nonpolar covalent, and I'll get to that in a minute. Now, if you look at the diatomic hydrogen example we've been using, and you calculate the change in electronegativity, you're going to get 2.1 minus 2.1 equals 0. So there is 0 change in electronegativity, which means that there is 0 transference, 0 ion formation, and that the electrons are being shared equally between the two atoms. Now, using the change in electronegativity and the Pauling scale of electronegativities, you've learned you can begin to make predictions about what types of bonds will form. Well, for covalent bonds that are non-polar, think of equal sharing of the electrons. We typically will see a value less than 0.5. And again, that's the change in the electronegativity values of less than 0.5. All right? This indicates that electrons are being shared equally between the two atoms. If you look at a greater difference in electronegativities, you get into something called polar covalent bonds. All right, these bonds form typically when the change in electronegativity is greater than 0.5, but less than 1.7. Now recall from the video on ionic bonding, there's also an area there between 1.7 and 2 where you need to look at the species that are bonding to decide if it is a polar covalent that has a very high change in electronegativity versus whether it is an actual ionic bond. And the key to that is simply asking the question, is there a metal involved? Because if so, usually that's just going to be your ionic bond. Are there two nonmetals? Then it's going to be polar covalent. So to recap the difference between these two, it's how equal the electrons are being shared between the atoms. Think of equal sharing for covalent. 5 Skittles for me, 5 Skittles for you. Equal sharing. For polar covalent, 1 Skittle for you, 4 Skittles for me. And that is unequal sharing. So that's one way to think of this. Again, you can use the scale at the bottom of your Pauling electronegativity periodic table. In polar covalent bonds, electrons are going to be drawn closer to the nucleus of the atom with the higher electronegativity. Think about me with my 4 skittles and you with your 1 skittle. All right, so I have most of the skittles closer to me. I have a higher electronegativity. And also remember, electronegativity is the ability of a bonded atom to attract valence electrons or shared electrons closer to itself. All right, so it's the unequal distribution that will result in what is called a dipole. Now, the prefix di means 2. What it is you get essentially the more electronegative species in the bond is going to have more of the electrons and is thus going to have a greater negative charge compared to the other species. The other species still has electrons, but less of them. So what you get is a dipole or a dipole moment, as they're called, that sets up between species. Let's look at an example here. Let's look at hydrogen chloride. Hydrogen has an electronegativity of 2.1, chlorine 3.0, so our delta En value is going to be 0.9. Where does that fall on the scale? Well, it puts us into the area of a polar covalent bond forming, unequal sharing among species. Chlorine has a greater electronegativity value and therefore has a greater ability to attract shared electrons to itself when compared to hydrogen with its smaller value of electronegativity. So what we see is a dipole forming where the chlorine has more negative charge than the hydrogen pole. Now this can be indicated a couple different ways, but usually the lowercase delta D is used along with a plus or minus sign, and that denotes or indicates a partial negative or a partial positive charge. Also, an arrow drawn pointing in the direction of the negative pole also indicates a dipole or a dipole moment in a molecule like hydrogen chloride. In covalent compounds that share equally. When they share equally, we're going to expect, again, to recap, a delta En value of 0.5 or less. So we don't see a dipole in a non-polar covalent species. Because of the way that these species are sharing, they are assuming a more stable configuration. They are satisfying the octet rule. Let's look here at this schematic that is comparing the number of electrons required and the number of covalent bonds that form. So think about going all the way back to +1, +2, +3, skip, -3, -2, -1, zip. Let's look at hydrogen. Hydrogen has 1 valence electron. Well, how many would it need to become more stable? 1 more. How many covalent bonds does it form? 1. Let's look at carbon. Carbon has 4 valence electrons in its outer shell. How many more would it need to satisfy the octet? It needs 4 more. So how many shared covalent bonds could it form? 4. See, by using this and looking at this, you're able to predict not only the number, but type now of covalent bond that can form among chemical species. Let's look at fluorine. Fluorine has 7 valence electrons. It needs 1. So how many covalent bonds can it form? It can form 1. All right. Now what's interesting here is if more than 1 pair is shared between atoms, then we get the formation of multiple bonds, such as double bonds and triple bonds. Lastly, I want to talk to you about network covalent solids. They are substances that are held together by covalent bonds, but the covalent bonds actually extend throughout the entire sample. They are one continuous network. Network covalent solids are incredibly strong, incredibly difficult to break because they are essentially one giant molecule. Examples of network covalent solids would be diamonds and allotropes of carbon like graphite and quartz. And as you can see from these schematics, they form these elaborate networks that extend throughout the entire molecule. So in this video, we've continued our discussion of bonding. You now know a little bit about collision theory. You know about ionic bonds, covalent bonds, and non-polar covalent bonds. I'll see you guys in class.